Now we'll consider friction forces when an object is moving in a fluid. The fluid could be a low density fluid like air, so here's a freely falling object in atmosphere. It could be a skydiver, or it could be an object falling in a liquid high density fluid. The object is falling slowly, and the friction force experienced by this falling object, by this object, is called a drag force. It's called a drag force. Now there are two types of situations we want to consider. For large objects, the drag force is proportional to the speed square, and this is true for large objects falling with high speeds in low density fluids. The second situation will consider is when objects are moving in, they're going slow or in a denser medium than air. So, for instance, uh, this object falling in water or oil, this won't achieve great velocities, and that'll be slow speeds. Okay, and in that situation, the drag force is proportional to the velocity, and this is Stokes' law. So we'll be considering two different situations. When the drag force is proportional to, we'll be considering situations when, so we'll consider drag situation proportional to velocity square, speed square, or drag forces proportional to velocity. So two different regimes. Okay, so the magnitude of the resistive force when a body moves in a fluid can depend on speed in a complex way. Okay. So the resistive force is proportional to the speed when small objects fall slowly, such as dust particle in air. So in that situation, it's this condition. For larger objects such as skydivers, the drag force is proportional to speed square. Okay. So when it's proportional to the speed square, the drag force is given by something called the drag coefficient, which is roughly between half and 2 the density of the fluid in which you're falling, so that would be the density of air, and the area of cross section of the object. So this area of cross section, the area of cross section perpendicular to your velocity. In this case, the area of cross section is much larger. Okay, so the drag is much higher in this case, times the speed square. Yeah. Now, since what this diagram is showing you is, so when an object is dropped, since the drag force is proportional to the speed, when you first drop it, the drag force is 0 and it accelerates downwards at g. Now, as it gains speed, the drag force starts increasing and the acceleration starts decreasing. And so the purple arrows are the acceleration, and you see the acceleration is decreasing as the object gains velocity. And once the acceleration goes to 0, the velocity becomes constant and the object has reached terminal velocity. So when it reaches terminal velocity, the drag force is minus the weight is 0, since the object is not accelerating anymore. And the terminal velocity can be calculated like that. It's equal to twice the weight of the object times the drag coefficient times the density of the fluid in which it's falling divided by the area of cross section. Okay, so this diagram shows you the velocity of a falling object as a function of time. The velocity increases, and once you reach terminal velocity, your velocity is constant. So here are terminal speeds of some objects falling down in air. Falling through air on Earth. Okay. So skydiver falling down with a cross-sectional area of 0.7 meters per second square has a terminal velocity of 60 meters per second. Again, that's roughly 150 miles an hour, and that's that cross-sectional area is this configuration. Okay. Raindrops So hailstones falling have a terminal velocity of 14 meters per second. So that's close to about 30-35 miles an hour. And so hailstones can be dangerous. And you probably don't want to go for a walk during a hailstorm. Raindrops, on the other hand, their terminal velocity is 9 meters per second, and walking in the rain would be fine. So now we'll consider situations where the object is small, going slow, or it's falling in a dense fluid like oil or liquid. And then the drag force is proportional to its speed. This is Stokes' law, and the other term, so 6 pi eta is the viscosity of the fluid. R is the radius of the spherical object that is falling. So for a spherical object falling in a fluid of viscosity eta, the drag force is given by that. And when it reaches terminal velocity, the drag force is equal to the weight of the object. And so you can actually do experiments like this. So take a long beaker of oil, drop a steel ball, measure its terminal velocity. So once it achieves terminal velocity, you can measure how long it takes to cover a distance. Distance divided by time will give you the terminal velocity. You can measure the radius of the object, and so you can solve for eta. This viscosity is the weight of the object divided by 6 pi radius times terminal velocity. So here's how you can get the viscosity of an oil, for instance. The Coriolis force, so it's a fictitious force that arises because you see things from the Earth's frame of reference, which is a rotating frame of reference, which is non-inertial. So anyway, here's how it arises. So here's the equator. As the Earth is spinning, points at the equator are traveling at about 1,000 miles an hour, and the poles are stationary. So as you go from here to there, the speed is decreasing. Okay. The speed of the Earth is decreasing because it has to go in a smaller and smaller circle over a 24-hour period. All right, so well, the air above that part of the land is also going at that speed. Okay, so now let's look at what happens when. So now let's erase this. So here's the equator. Here is this parcel of air going at 1,000 miles an hour. This parcel of air, let's say, we'll just make up numbers, going at 400 miles an hour. And if there was a low pressure here, and this parcel of air moves toward there, and that parcel of air moves towards here, this part is moving at, this Earth is moving at 700 miles an hour, so this will lag behind. This is still going faster, this will get ahead. So a low pressure in the northern hemisphere, you'll have a counterclockwise rotation, and similarly you can you'll see that a high pressure air moves away from a high pressure, and you'll get a clockwise rotation. Okay, so this is the Coriolis force. Even though there's no force, it will appear like you have a force making the air turn. That's because you're seeing things from a non-inertial frame of reference. Here's an interesting application: geese fly in a V-shape formation, because if you've ridden bicycles, the geese in the front face the most drag, but these guys face less and less drag, and so the geese will fly in this formation, and the lead geese takes turns. Every geese takes turn to being the lead geese. So while you're here, anywhere here, you're working less hard. You're working the hardest there. Okay, and also apparently this formation is good for communication. Anyway, if you collectively fly like this, you collectively reduce your drag, and use collectively use less energy. So it's a good strategy. All right, that finishes that chapter.